So the next code example I want to do is we're going to build a stack. And specifically, we're going to build a stack that's completely broken. So let's go ahead and open up a sequential stack. And we're going to get some headers. We don't need pthread yet because we're writing a sequential program, but it's going to be a parallel program in a second with threads. We want studio, we want assert, and then for some reason I have a unistd header in here. We'll find out why in a second. So here's our stack. It's going to have 5 slots in it, and it's going to have a pointer, and the pointer points to the index of the next empty slot in the array. So if the stack fills up, stack pointer is going to be 5 because that's out of bounds of the array. That's fine. We've got some simple operations on a stack. The stack operations are push, which is going to take an integer, and pop, which is going to return an integer. So this is pretty straightforward. We say stack. We're going to take the pointer and we're going to increment afterwards. So we take the current value as the index, and then after we've taken that value, we'll increment so the next operation works on the next one. We'll set that to the value, and then we're going to return our stack. So our stack pointer points to the next item that we're doing, so I think we want pre-decrement. Right, we want to decrement and then return the value. So that's simple enough. Let's go ahead and give this a quick test. Int main, int c char pointer av. So we're going to push onto the stack our number. Then after we've pushed 5 numbers onto the stack, we're going to say, we're going to pop all the items off the stack. Then we're just going to print those items out. So this program actually should be pretty good. Let's see if we can get it to work. And then quick, go ahead and predict what this is going to print out. Bonk. Alright, so it prints out the numbers in reverse order. We pushed the items onto the stack in forward order, 0, 1, 2, 3, 4. We pop them off the stack into the stack, so we get them in reverse order. It prints 4, 3, 2, 1, 0. Now, question. If we increase this value, so const int and n is 5. We make this 10. It's still going to compile without any warnings. What's this program going to do? So the first option is it's going to print out the values as expected, so from 9 down to 0. The second option is that it's going to crash. And then we have the question of why does it crash? So go ahead and predict, do you think it's going to work or it's going to crash? And if it's going to crash, why? Sequential stack, it worked. Interesting. So we have a stack of 5 items, and we have pushed 9 items into that array. They all fit, and then we popped them all back off, and it all worked fine. Will 100 items work? Sorry, not 100 there. We want 100 down here. So we have an array of size 5. Can we stick 100 items in it? Why, yes. Normally that wouldn't work. So, question. Can anyone predict what the highest number that I can put here before this actually crashes is? We only have a stack of 5 items. We're going ahead and putting way more than 5 items on there. So the prediction that I want to get from you guys, and go ahead and pause if you want more time to make a prediction, but the prediction that I want is that we can get 4096 divided by size of int items to fit on this stack. So 4096 is a number you should recognize. That's the size of a virtual page. And so that's the minimum size of a allocation with mmap. And if you remember correctly, these two variables up here are in our .data section of memory. These are global variables. This one's even global and initialized. And so when this program is compiled, a data section is allocated in the executable, and this data is sort of mapped in from the executable file into memory, and it's mapped in as one page. We only have these two things to put in. There may actually be some other stuff that's hidden in there, but we only have these two things that we can see. And so we should end up with 4096 minus size of int for stack pointer, all of that divided by 4. So that's going to be 1024 minus 1. So the expectation is that 1024 should definitely crash. Segfault. And then the expectation is that 1023 should work. Segfault. Alright, so the reason that's failing, at least according to this story I'm telling, is that this is the stuff that we can see in our data section, but C is putting some other hidden stuff in the data section that we don't know about. So in that case, if we put in like 900 here, success, 1000, success, 1010, segmentation fault, 1005, success, 1008, success. Alright, so 1008 works, 1010 segfaults. Our prediction was that 1023 would work, but there's other stuff in there. Alright, so that's just a distraction from where we wanted to go, but that's important to keep in mind when we're messing around with just memory in general, is that segmentation faults are the result of trying to access pages that don't have the appropriate prot read or prot write flags set in the page table. The minimum allocation is size 4096, so we don't necessarily get segfaults accessing things that are accessing pages that we know are not full. But let's go ahead and take this one and copy our sequential stack over into a parallel stack. And what we're going to do is, I mean, this isn't really a parallel stack. It's going to be a concurrent stack. Let me be clear. So the stuff that we want to add here is, we want to create a thread. So our thread is going to pthread t. We're going to have two threads, two additional threads. So we're going to have two threads that are going to be pushing items into the stack, and then we're going to have the main thread pop items off the stack. So then we're going to say for int I is 0, I is less than 2. Don't need any of that nonsense. So int rv pthread create. We need to then pass in this thread slot in the array. And then we want to pass in I'm just not even going to pass in an argument here because I'm not super worried about passing data here. We're just going to have it produce some stuff. We're going to say that we're going to... So we know we can get away with like sort of overflowing by a lot, so we'll start with an NN of 500. So then we've created our threads. So then in our producer thread function, void producer thread, we have an argument. We don't care about it, so we don't even need to name it. We're going to do this. So each thread is going to produce values and push them onto the stack from 0 to NN. NN is, well, from 0 to 499. And then in parallel here, we're going to consume 2 times NN. And then I mean, this won't succeed until the thread's done, so we don't even need to bother about joining in this particular example. So we'll compile this. Parameter name emitted, fine. You should be able to get away with that, but I'll call it underscore arg because we're not going to use it. So we run our concurrent stack program. And what we get is sort of strange results here. So it printed all the numbers from 500 down to 0. Then it printed all the numbers from 500 down to 0. And then it exited. So we didn't really get that much behavior as far as concurrency. So I'm going to go ahead and put in a useSleep call here. So we're going to have it sleep for 1 microsecond. And the reason I want to do that is just to give a chance for both producer threads to start up. There we go. So without the useSleep, it just happens sequentially. But with the useSleep, we suddenly have a problem. And the problem is that we get 0, 0, 0. We get a whole bunch of junk data. Why do we get junk data? Well, this should be obvious if you think about it for a second. But, so thread 0 pushes a 0. Thread 1 pushes a 1. And then they're both going to try to sleep for 1 microsecond, which is long enough that the main thread gets to start going through its pop loop. And this is popping numbers with nothing slowing it down at all. Whereas we have a slight amount of slowdown here, and so popping is going to happen faster than pushing. And so that stack pointer is going to end up dropping down below the below 0. We're going to try to look in negative indexes in the array. And although we have a bunch of space after where that array is allocated in the data section, it's allocated near the beginning of the data section. And so before it, and in fact, I think a lot of what we're seeing here is that excess data that we that was taking up space in the data section. I think it's allocated before our 2 variables in the data section. But once we get past that stuff, we get out of the page and we get a segmentation fault. So in order to try to figure this out, I'm going to go ahead and slow this down. So we're producing one thing every, well, we're going to produce 2 things every microsecond, and then we're going to consume 1 thing every 3 microseconds. So with this version, we should get a nice mix of yeah, they're kind of mixed together. You can see that we get 228, 219, 227, 237. Our numbers are sort of intermixed. Both producer threads are producing into the stack. The one consumer thread is consuming out of it more slowly, and it all sort of prints out. This is the sort of output that is a perfectly reasonable outcome of this particular thing. So why does the version, how do we fix this version where we don't have any sleeps? Sorry, how do we fix the version, the version where we don't have any sleeps runs sequentially, which isn't interesting. How do we fix the version where we are consuming faster than we're producing? Because that's one of the sort of conceptual possibilities, and actually we could make this happen without artificial sleeps by having two consumer threads and then having the main thread be the producer thread, because then the consumer threads would run ahead and we'd be decrementing faster than we're incrementing, and we would underflow our array. And so the first thing that we want to do here is we have concurrent access to shared memory. So we have some risk of a data race, and we could even conceptually have a data race here, although it doesn't look like we're getting sort of directly data race related bugs, but we should fix the potential data race. We're breaking the rules, and so we should instead follow the rules, and the way we're going to do that is by inserting a mutex. Now, a mutex is the thing that the pthread library comes with that is a built-in lock. It's not like a semaphore where it's just something that we can use ourselves to construct a lock. A mutex is always a lock. Mutex stands for mutual exclusion, which is the thing that a lock does. So then in order to use that pthread mutex, before we start having concurrency, we want to initialize it. So we're going to say pthread mutex init. We're going to pass in that lock. We're going to quickly look at the man page. So we want the mutex. We want some attributes. The attributes can just be the integer 0. That's fine. So now we have our mutex initialized. And now around our two operations, we can go pthread mutex lock to lock the mutex, and then we can do pthread mutex unlock to unlock the mutex. So now this access to our shared data is protected by the mutex. Similarly, down here we can go pthread mutex lock, we can go pthread mutex unlock at the bottom, and now we should be able to run this without worrying about data races. It froze. Do you see the bug? So the bug, of course, is that we're returning before we unlock the mutex, so we need to do something like this, where we do the operation on the shared memory, load it into a local variable. This is probably going to be a register, but that local variable we can't have data races on, and then after we unlock, we return the local value. Sorry, GCC. All right, so now we still have the segmentation fault, but I assure you, we've solved the potential of data races here. But what we really want to do is we want to make sure that we satisfy some preconditions before we do these operations. So stack push has an important the important one that we're worried about here is stack pop. And so we have this precondition for stack pop. And the precondition is that before we pop, there has to be data on the stack. If there's not data on the stack, then this code that we have is going to decrement the stack pointer and therefore underflow the stack. We'll start accessing memory before the array here in memory, and that's not what we want to do. And so we have a tool to help us ensure these preconditions. The tool is called a condition variable, and what it's going to let us do is it's going to let us check for these conditions, and if they're not met, what we can do is we can block until someone else causes the precondition to be met. So the stack pop is getting called down here by our consumer thread, and the consumer thread isn't going to solve this problem of not having data on the stack. It has to wait for one of the producer threads to produce data onto the stack. So that's the condition that we're looking for. And so since the stack pointer is going to point to the next empty slot, we have to have stack pointer is greater than 0. And similarly, we have a precondition up here. Precondition, there is a free slot on the stack, and that is that the stack pointer is less than next empty slot. Wait, so if the stack pointer is, it's less than, right? The stack pointer has to be less than 5. Because the stack pointer is 4, we're pointing at slot 4, which is the top slot in the stack. I really want there to be an equals to in one of these cases, but I don't think there is. I think it's just greater than 0 and less than 5. I could be wrong. We'll see if it works. So a condition variable is something that goes with a mutex. So pthread cond t, I'm going to call it cond. We need to initialize the thing with pthread cond init. It also take attributes like the mutex. So a condition variable is something that goes with the mutex, and it allows us to have logic that is going to block on sort of arbitrary conditions where the condition is related to the data that's protected by the mutex. So we have our shared data, which is this stack structure. The shared data consists of 2 parts. We have the stack variable and we have the pointer. This could be a structure. I just didn't define a structure because it's 2 globals. Those shared data is protected by this lock, and associated with that lock is this condition variable, which we can use to handle checking these preconditions. So the pattern that we need to use here is while the stack pointer is greater than or equal to 5, the condition is not met. But before we can ask this, we're going to take the lock, because we have to access the shared data to check it. So we're accessing the stack pointer. First we take the lock, and then we check if the condition is met. If the condition isn't met, we're going to wait. So we pass in our condition variable, and we're going to pass in our lock. And what this says is our condition wasn't met, so we have to wait for someone else to solve this problem for us. Someone else has to change the shared data, and once someone has changed the shared data, that may have fixed the problem that we're waiting on. It may have caused the precondition to be satisfied. So someone else, when they change the shared data, is going to notify us through the condition variable. We will wake up. Now we must be in a while loop here. Anytime we call pthread cond wait, we must be in a while loop, because condition variables are allowed to sometimes have spurious wake-ups where this function is going to return even though the shared data didn't change. But when we return from here, we recheck the condition. If the condition is satisfied, we can continue. But if the condition is not satisfied, we will wait again for someone to fix the problem for us. So the only person who can fix the problem for us is the stack pop thing. That's the only thing that mutates it. So after we've changed the stack pointer and extracted a number, we're going to do pthread cond broadcast, passing in the condition variable. And that's something that we do while we're holding the lock. And this is going to notify anyone who's waiting on this condition variable that the shared data has changed, and they should wake up and check to see whether the change to the shared data has satisfied the condition that they're waiting on. Now, symmetrically, we have this condition here where the stack pointer is less than or equal to 0. We're going to wait. And then the thing that can fix that for us is push. And since we have these 2 different conditions that we're waiting on for the one condition variable, we have the question of whether we'll ever have additional spurious wake-ups where somebody's waiting on this condition and then the broadcast occurs. And the answer is probably not. Either the stack is full and people are blocking on it, or the stack is empty and people are blocking on it. The stack can't be full and empty at the same time. So there's our example with the condition variable. And what that should do is make it so that rather than overflowing or underflowing, our processes are going to block. And so we compile that and run it, and we end up getting, let's go all the way up to the top to sort of see our start here. Okay, because we have this 1 second sleep on the producer threads, they're just sort of, both producer threads are producing at the same time, and then the consumer thread is consuming completely in order, no overflows or underflows, everything works. Let me go ahead and compile with that uSleep sort of before the loop and see if I can get any sort of, there we go. This is the wrong one. So you can see here that the numbers for the two producers are sort of mixed together because they're being preemptively scheduled. But, and we start with the number 4, so it looks like one of the two producer threads filled up the queue. Then the consumer thread started consuming, and it's consuming out of the queue, and then, I don't know, probably we're consuming slower than we're producing, so probably the stack is staying full basically the whole time, and just as we produce things into the queue, they're getting immediately pulled out. So that is an example of condition variables and how with threads we can solve this sort of problem like having a stack where sometimes we need one process to block waiting for another process to, or we need one thread to block waiting for another thread to do stuff. And this is something that's an alternative to semaphores for solving some kinds of problems. Condition variables are kind of more general than semaphores, but you may be able to build one using the other. It's worth thinking about. Can you build condition variables using semaphores? Can you build semaphores using mutexes and condition variables? This is going to be essential for homework 7, since in homework 7 you will be building a barrier using a mutex and a condition variable, or maybe you need more than one. So good luck on the upcoming homework, and I'll see you in future lecture videos or in our class discussions.